So next up we have Richard Green from Baxi Potterton Myson. Richard's been working in the gas and heating industry for 34 years, having served his apprenticeship with British Gas and then worked for British Gas as a service engineer. He then worked as a self-employed gas boiler specialist before joining Canon as a service engineer. In 1998 he joined Baxi's technical support team as a technical advisor before joining Baxi's training team as a training officer in 2002.
You make me sound like a gypsy. Just let me get this started. Good morning. Thank you for taking the time to partake in this presentation about the role of boiler control. Excuse me. The presentation will take about 20 minutes, and I'll do the sort of factor in a question and answer session at the end, but what we'll do is we'll skip that because I'm aware of the time. If anyone else can ask me any questions at the end, I'm on the Baxi stand, so you can come and see me then. We're being constantly bombarded through the media with messages relating to scarcity of carbon-based fuel supplies, the security of supplies, and the inevitable price rises that we're going to incur in the pocket. And energy security affects everybody. The conservative estimate is that fuel prices are going to increase by every year for the next 16 years, and depending on which periodicals you're reading, anywhere between 16 to 25% fuel price increases. So what's happening now is a lot of consumers, savvy consumers, are switching on and looking for low-cost solutions to implement and reduce the carbon-based fuel use but still maintain their comfort conditions. So this gives the opportunity for switched on heating installers and developers to pick up additional revenues for their businesses. This is where low-level controls comes in. Now, you've been going through the process with your domestic energy assessment process, looking at improving controls, and when it came out in the UK, there was this is not a representation, by the way. There was a lot of confusion with regards to some of the terminology that's being used within that documentation. One of the key things was boiler interlock. And a lot of people thought boiler interlock was a separate piece that was stuck onto the installation. It isn't. What boiler interlock is, how we would understand it, is a series of controls which turn off the heat source in the event that there's no heat demand, the heat demand's been satisfied. So, for example, full programmer, room thermostat, cylinder thermostat, motorised valve setup. That is a basic practice control package which gives the boiler interlock. We could further enhance that by putting thermostatic radiator valves in the room to give individual room control. We could put in the change the programmable room thermostat to a programmable room thermostat, which gives flexibility on individual times and temperatures, so we're controlling the temperature when we're in and we're out of the property. We can also expand by utilising motorised valves to zone the system and actually provide heat for occupancy periods in certain parts of the property, so we're not overheating heating the whole house up together. Advanced controls, and I use that word advisedly, I mean the level of sophistication isn't that much with things like delay start thermostats. It does what it says on the tin. It's a thermostat outside the building, and when we reach a threshold temperature, it delays the start of the heating system. So if we set it to 5 degrees, say, when the air temperature is above 5, then basically what it does, whatever's been programmed in, it holds the boiler off for 10-15 minutes. And if you're working on an off, 2 days cycle of 2 on-offs, half an hour a day, realises a significant reduction in energy over the heating period. But one of the most underutilised controls options that we have is weather compensation. This is extensively used throughout Europe, and they pick it up and run it. In countries like Denmark and Sweden and Germany, it's standard practice, it's basic practice to put on weather compensation. And in the UK and Ireland, we're fairly reticent to pick up and run with this technology. And I believe personally that that's something to do with a lack of understanding of its application and the commission and the setup. Weather compensation, in a nutshell, excuse me a minute, is an outside temperature sensor which basically modulates the flow temperature to the heating system to maintain comfort conditions. Or even simpler than that, if you want a simple explanation, it is, as the outside temperature drops, my radiators get hotter. Most modern equipment, modern heating boilers now incorporate a connection to wire a weather sensor directly to it, so we can modulate the output of the boiler directly. But we need to understand the application, and we've got to go back to basics with design consideration. Now I was always taught the BRO principle, and that's BRO, B being your heat input, your maximum heat input into the system, R being your room temperature, and O being your outside design temperature. And for a typical wet radiator system, what we used to work on was 82 degrees flow temperature to maintain 21 degrees comfort room temperature with an outside temperature of -5. So what we'll do is we'll graph that out. So I'm going to achieve 21 in the room. And when the air temperature drops to -5, the rate of heat loss to the property is accelerated. So we need to put a lot of heat into the system. So at -5, we need to put in there 82 degrees C. So we've got a target temperature point, the little red dot. As the outside air temperature increases, the rate of heat loss to the fabric of the building slows down. So I don't need to put loads and loads of heating into the system. So what we can do is we can reduce the temperature on the boiler thermostat. So at 20 degrees C, I want 25 degrees flow temperature coming out of the heating unit. So we've got another point down there. We'll join those two lines up, and I'm going to graph it and give it a name, 1.5. It doesn't mean anything at the minute. So most weather compensating kit, most radiator sizing charts were based upon these figures. So what we go and measure up, size the radiator to suit the room, okay, put that in, fill the system up, turn the boiler thermostat up to maximum, and while we're commissioning the system, the customer comes around and goes, blimey, wow, these radiators, they're taking my skin off, and we go, yeah, alright, fantastic, give me the money, I'll see you later. And we leave the property, and we don't hand over properly. And we don't actually explain that take your skin off hot is -5 outside the building. So when the weather turns, when it goes freezing, and I'm from Lancashire, and the laws of physics do not apply in Lancashire because freezing is 10 degrees C. So that's when my wife turns the boiler thermostat right up full. So what happens is at 10 degrees C, all I really need with a weather compensated system, or going to my radiators rather, is 55 degrees C. And that will still maintain my comfort conditions because of the rate of heat loss through the building. But what's happening is, I'm walking into my house in winter, it's like walking into a furnace that's got all the doors and windows open, lad. Okay? And this is costing me a lot of money. Not only is it costing me money, it's costing me money unnecessarily for being uncomfortably hot. And the reason for that is I work with a condensing boiler, and what we need to remember with a condensing boiler is the magic temperature, which is 57 degrees. Because if you can keep return temperature below 57 degrees, you maximise your condensing mode, your fuel. So whatever you're putting in, you're pulling back as much heat out of it as possible. I've just put together a very simple schematic. So as we're looking at this schematic, the two blue lines are basically what my wife does. She's turning the boiler thermostat up to maximum, and we get overly hot because the flow temperature is averaging out at above 70 degrees C. And if we work on a standard system differential of 11 degrees C, then the return temperature is coming well above 60 degrees C. So we're working like a high efficiency boiler, but we're not maximising fuel use. Weather compensation, if I had a weather compensated system, is basically like somebody having a hand outside the building. And as the temperature drops, we turn the boiler thermostat up to maintain comfort conditions with increased heat loss to the fabric of the building. And that decides we don't actually need maximum temperature, we can actually deliver the comfort that the end user requires by reducing the flow temperature. If we're working on 60 degree flow temperature, on a design differential of 11, we're coming back in at well under 50 degrees C. So the boiler is condensing, we are maximising our fuel use. Plus, we're not getting massive overheats and then massive sessions of low temperature. We're not getting too hot, too cold within the property. Our boiler's cycling less, so if you reduce the sort of cycling of the boiler, you actually increase your efficiency. Weather compensation. Simple, low cost, easy to install mechanism. Monitors the outside temperature, like we said, has a recognised DEAP benefit. It's about 3% in the UK, that'll probably be the same over here in Ireland. No service and maintenance required. It's a fit and forget. Low voltage cabling, no specialist wiring skills required. But one of the key things we need to remember when installing is installation criteria. Make sure it's installed properly, make sure that it is commissioned properly. Right, so the first two factors we need to be aware of is location and levels of insulation within the property. Where does the sensor go outside? The sensor goes on a position where we're not getting extremes of temperature. The sun rises in the east, climbs due south to midday, that's hottest point of the day, then sets in the west. So a north to northwest facing aspect is the ideal position for the weather sensor. Height from the ground, at least 2.5 metres. But if you've got a big property, 3 stories building, let's say it's 10 metres, it's half the distance from ground floor to eaves. So you position it at 5 metres. Insulation plays a big part in the performance of heating systems. The less insulation there is in the property, I need more heat, I need a high surface temperature heating system in there. If you've got a really well insulated property, then you don't need as much heat, so you can go to low surface temperature heating systems. So if you go back to our graph, and let's turn around and say I'm building a project, it's a super insulated property, Kevin McLeod's going to turn up with all the Kingspan, and we're going to build this house, low surface temperature underfloor heating system. At -5, I don't want 35 degrees banging out to the, 82 degrees banging out to the radiators, so we can drop the flow temperature down to 35, so we end up with a line down there. Let's say I live the opposite side of the coin is turn of the century, red brick, terraced sieve that can't keep hold of the heat very well. Okay, it can't retrofit a lot of insulation in there. At 0 degrees C, I may need 82 degrees C going to the radiators. So I've got a steeper curve. And what we find is we get lots of different curves for different central heating systems in different house constructions. So all this is looking a bit confusing. So what we'll do is we'll give them some ID numbers. I'm on site. It's the first time we'll put a weather compensator in. Let's assume I've got a north to northwest facing position. I'm not so sure which curve to set it to. So what I'm going to do is I'm going to set it to the steepest curve there. So what I've actually done here is I've over-egged the system. I've put more heat in than was designed to go in. Have I done anything wrong? Now we're saying we designed it -5 gives 82 flow temperature. But now what we've done is we're turning around and saying at 0 degrees C gives 82 degrees flow temperature. So realistically, how many days in Ireland is it below 0 degrees C during the heating season? And the answer to that is not many. Right? Let's be over generous. Let's say 6 weeks. Okay, so for 6 weeks of the year, what we've got is that should have been a euro sign, by the way, I apologise about that. We've got maximum fuel consumption. And this is basically equivalent to the customer turning that thermostat up to maximum themselves. As they, what are they saying? What's the return on that? It's sitting up there, we're burning maximum fuel consumption, fuel bill's €1,000. But what happens is, if the customers turn that up themselves, the next thing is, if the air temperature goes above 0 degrees C, if they forget to turn that thermostat down, it's still then costing them more money on the fuel bill. But what a weather compensating system does is it reduces the output flow temperature of the system while still maintaining comfort conditions. So what we actually start to do is reduce our consumption. And over a period of use on the heating system, what we turn around and say is, with a weather compensator, if you put a thermostat in where there hasn't been a thermostat before, you can get somewhere between a 6 to 10% benefit or reduction on fuel use. So let's be conservative. Let's say 6% reduction on your fuel bill. So €1,000, 6% reduction, €60. The actual typical cost of a weather centre is about €40. So for a low cost investment, you can get a big return. If your fuel prices stay the same over the next 10 years, you're going to reduce your fuel consumption by €600. If you put that offer on the table for most people, they'd snap your hand off. The problem comes in explaining and handing over and making sure we educate the end users. So, how do we do that? Let's go back to the commissioning scenario. Hands on the radiators. Wow, this is hot. This is taking the skin off. We say, yeah. Next time the radiators are that hot, if you look outside, it'll be snowing, it'll be freezing, it'll be a stay indoors kind of day, right? But the day after, it might get one of these good walking days where the sun comes out, you can put a jacket on and go for a walk. But you put your jacket on, you put your hand on the radiator and you notice that actually the radiator's hot, but it's not as hot as it was the day previous. And that's because the system is automatically adjusting, it's made the decision it doesn't need to put that much heat in to maintain your comfort conditions. But the customer might turn around and say, well, yeah, that's all right, but I'm cold. You say, well, if you're cold, turn the thermostat up. But don't do what my wife does, big sweeping 10-degree leaps up and down. Turn it up a degree. If you've got a digital thermostat, half a degree, so we're very susceptible to temperature changes. So, once you find your comfort condition, because comfort is different for everybody, right? 20 degrees for me is like being in an oven. I'm sort of 18, 19 degrees kind of guy. And we'll wait till later if anybody's the same temperature as me. Alright? So, once you've found that, leave it. Leave it at your comfort temperature, and then what happens is the system will automatically maintain, as you're walking in and out of the house, you're always getting your design temp. If these people are a bit switched on and they know what their comfort temperature is, we want 21 degrees, so they're switched on, or there's a 6-year-old in the house, what I'll do is I'll show them how to change the curve. So instead of going about a steep curve, I'd move it and I'd change it to that position there. And by doing that, what we've actually done is we've reduced our fuel consumption and therefore gained or achieved a greater reduction on fuel costs. So as a general rule, and again, if anyone wants to talk specifics, again, come and see me later on the Baxi stand. The steeper the curve, what you're looking at there is high surface temperature heating systems, poorly insulated properties. The lower the curve, we started to talk super insulated properties, low surface temperature heating systems. In the middle of these, like low surface temperature radiators. That's a general rule. The science bit. Okay, going back to our design criteria, right? There's a calculation to work out the heat curve. So what we've got, the heat curve is design floor temperature minus design room temperature divided by design room temperature minus outside design temperature. So we put the figures in we've been working to. 82 minus 21, 21 minus 5, which gives us 61 divided by 26. When you minus and minus, it becomes a plus. I never understood that, but it does. Alright? The heat curve then is 2.34. So looking at a typical weather compensating diagram, we've got all these curves on, and we've already calculated that we need to be on curve 2.34. And the nearest one, where that red dot is now on the top line, we've got a choice of two. We've got 2.5 or we've got 2.25. And whatever the mechanism is you set it on the manufacturer's kit. Bear in mind, a steeper curve, more heat. A lower curve is less heat or a greater fuel saving. And again, if you want to work on the side of caution, you set to 2.5. If the customer wants to save as much money as possible, you go to 2.25. So there are benefits to retrofit applications, one-off installs, but there's also significant benefits in helping specifiers and developers achieve the targets that set out in the domestic energy assessment process. So what we've got all there is a sort of a typical example of a new build property. 145 square metres floor area, semi-detached, backstop U values, natural ventilation. The heating system, gas boiler. So we put up there a Baxi Eco Blue system, 18 kilowatt unit, because it's the best on the market, just not throw that in. With a wet radiator system and a wood burning stove, which is offsetting some of your heating load. We're also making the assumption that the south-facing roof, we're going to put PV array on there at a 30-degree angle, so we get optimum performance from any PV kit that's installed. And within the domestic energy assessment process, there's a table here which is basically showing the levels of controls. So I'm not going to go all the way through, we'll do top and bottom. Top, basically there's no time or temperature control fitted to the system whatsoever. So basically flying lead, plugged in, boiler's running. You can still do that on the DAAP, but to meet the targets you'd have to install or put into factor into the build costs 3 kilowatt PV array. which is a significant chunk of money on a new build property. If we go to the bottom of that list, you've got a best practice weather control system, so you've got full programmable room thermostat, TRVs, cylinder start, and a motorised valve setup with a delay start timer and a weather compensator. And that reduces our PV requirement down to nearly a third, 1.25 kilowatts, which again is a significant reduction in build costs. So there are solutions. Baxi has got products available to help you achieve these targets. In summary, it's easy to install. Low voltage cabling means no additional electrical skills required, so it's plug and play connections in most instances. No service and maintenance required. No moving parts. Carbon saving. As a recognised benefit under your domestic energy assessment process. Boiler fires less frequently, which means less cycling, which improves the efficiency of the boiler. Low fuel consumption. Boiler modulates down to lower temperatures and therefore condensing more, and again maximising any fuel input you're putting in. So that's the end of the presentation. Again, I'd like to thank Heat Merchants for giving us the opportunity to stand here and talk to you today. If anyone wants to pick up any specifics, please see me on the Baxi stand. Thank you for your time.